Hello, today I'd like to continue our trigonometric session, and we'll also take a look at complex numbers in a way in which I'd like you to imagine them, which I consider the right way, one of the right ways, but at least that's one of the right ways, and not one of the many wrong ways. Well, I didn't mean that there is a wrong way to think of complex numbers, but there is a wrong way to shape own thinking of complex numbers, even when they could be taught in the right way, in the similar way. Well, doesn't matter much. Let's continue with trigonometric functions. By the way, if I'm writing too slow, you could just put the pace of the video of YouTube on 2, so you can change the pace of the video and you could just set it to 2, or maybe to 1/2 or something, so you could just change the pace. If I'm writing or speaking too slow. Trigonometric functions. So recap from the last time. Last time we have realized that the generalizations of cosinus and sinus to the general angles, which we now measure in radian, that is, we measure them in the units that correspond to the arc length on the circle, instead of measuring them in degrees. That is the more customary mathematical way. If you recall, if we have an angle alpha, and we can measure this angle simply as what part of the whole circumference the corresponding arc length which this angle makes out, right? What part of the circumference, right? And that was alpha radian, but we don't use the unit, we just consider it as a number, right? And we have realized that generalization of cosinus and sinus to general angles works simply via coordinate system. If we have a point on the unit circle, this point just has the coordinates cosinus x, sinus cosinus alpha. Of course, the x coordinate is cosinus alpha, and the y coordinate is sinus alpha. And this is just exactly how we define general cosinus and sinus. That is, for this angle alpha, for this angle beta, whatever, the coordinates of these points, which are defined in itself, are defined to be cosinus alpha and sinus alpha. That is, if we take cosinus alpha, then we just take the x coordinate of the point P, where this is P, Px, Py, this point, which is defined by this angle beta on the circle circumference. It has two coordinates, Px, Py. We define cos of this angle beta as cos beta is exactly the x coordinate of this point, and sine beta is exactly, and this is a definition, and sine beta is exactly the y coordinate of this point. Well, and from here, the way to looking at the graphs of functions of cosinus and sinus is not that far. We just do the following. We consider our unit circle. We consider our angles beginning by the 0 angle, of course, 3.10. And we now go to the coordinate system. Let's say, well, of course, it doesn't matter what I call it, but let's call this coordinate system x prime, y prime, and call the coordinate system where we will graph it. And by the way, let's make it larger. Let's make it larger. Okay. I suck at drawing lines, I see. Okay. Drawing straight lines. In whiteboard, you have the advantage of the ability to draw really large, right? We use this advantage to the fullest. Right, so we now have our two coordinate systems, and of course, we have same units, they are identical except they have different names, right? I could have drawn it in the same coordinate system, but that would be rather confusing. You don't need to distinguish those coordinate systems in your mind. They are exactly of same structure. They are just drawn now as different coordinate systems to have better visual, right? Okay. Now we go to the point 0 and we want, for example, to draw the graph of the cosinus, right? We go to this point 0 and now, oh, by the way, of course, I don't mean it like that. This is x also. Now not x prime, just x. And this is y. Right. Now we just go to the 0 point on this coordinate axis, and what would you think would be now our x coordinates here when we want to have graph of cosinus or graph of sinus? What would it depend on? Of course, not on degrees. You probably already know that it does not depend on degrees, but what would be the argument? The argument would be exactly this arc length, by which we can also identify angles as we have seen here. And this arc length goes like that from 0 to 2 pi in that direction. That's important. So 0 to increase, 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 increase. So along this circle, it totally increases the whole time. You could imagine that this circle is now put on the plane, and it is just a line, just that this line has this funny shape of the circle, right? And it goes in this direction. Also not the usual direction. Usually we would go on the line that is horizontal in that direction, but here we just go in this direction. We could also define our normal numbers in other direction. Wouldn't change anything, actually. Well, only the pictures would look differently. Yeah. So we do that, and now we go in the circle, and there the argument rises from 0. Here we have 0. Let's call it alpha, whatever. And it rises, it goes. And here it goes and reaches 2 pi. And 2 pi is on the plane, it's same point, but what we think in mind that here begins another circle that lies exactly on this first circle. And here it goes, of course, in the plane that is pictured all by the same circle. And this is important, that the points stay the same, but we picture in our mind another circle that lies exactly on this one covering it. And here we reach this point, but we reach this point, so to speak, on this circle that lies on the first circle, and we go further from 2 pi to 2 pi plus little epsilon, and go, 4 pi. Another circle begins. So actually, you could think of a spiral Of course, the geometric or the convention is that the geometric points are the same. We rarely really consider the spiral, but what is actually happening conceptually, that is a spiral. And I mean spiral with same radius. It just that's how you see it from above, right? You have that spiral, you have first circle, you go like that, and then another circle begins from here, and this circle is kind of higher, and then another circle begins from here, right? All the circles with same unit radius, we are on the unit circle, remember that? But yeah, actually, truth of the matter is we are talking about spiral. And now we could go from 0 in this direction to pi and continue to 4 pi, then continue to 6 pi, and so on. But of course, as you know, we have also the negative area here, and we have also to graph the graph somehow in the negative. If you want to have a proper function that takes any real number and gives something in return. So we could go also in other direction. That is, here we start by 0, and we go, and then we go into the negative. And here, same geometric point, but spiral goes downwards. And here we go 0 minus pi divided by 2, exactly same as here, but here pi divided by 2. Here, of course, pi, minus pi divided by 2 is exactly like here. You go in this direction 1, you go in this direction symmetric -1, and your numbers will repeat with minus. Here same, you have 0, here you have minus pi half, here you have minus pi, and so on, right? So, but same points in the plane, it's same points, just conceptually you kind of go on the spiral downwards on those ever lower circles, lower only in the sense that the interpretation of their points is we go into the negative, right? Minus pi, here we reach at some point minus 2 pi. And already here, you should pay attention that this point, now this single point 1, 0 in the plane corresponds, or kind of corresponds to angle 2 pi, to angle 0, and to angle minus 2 pi. Keep that in mind. Then we go, if we continue in this direction, or downwards our spiral, imaginary spiral, of course. Not in the sense of imaginary number, but just imaginary spiral. Then we go, of course, to minus 4 pi, and then all angles continue to minus 6 pi, and so on. So actually, the unit circle transforms conceptually into a spiral that goes upwards and it goes downwards. Yeah, maybe it's exactly a wrong way around, but yeah, you remember how to draw the spiral, right? If we go into the positive direction, then we have to go like that, right? So what I would do would be going like that, right? I go like that, go through my circle, go like that, go through my circle. Okay, but now in the negative direction, I go like that. So what we see here, you could think of that way, is the projection of the spiral of angles. But geometrically, it's all same points, and you have just to know that here we start new in negative and in positive direction, and you have just to know where we go into the negative and where we go into the positive direction. I know that might be a lot, so pause to think about it and internalize that properly. Just understand that it is our convention that we interpret the points of on the circle in that way, and that we interpret similar same points to correspond in this sense to different angles, and then continue. Okay, Knowing that, it is very easy to graph something like a sinus or cosinus, because what it is just, well, in 0, I know I have to read the coordinates at the point 0. So I have to read cosinus 0, the coordinates, in the coordinates at the angle 0. Because here, as we said, the argument is the angle. So the variable of which the cosinus will be drawn is, of course, the angle. And of course, the angle in the circle units. Not in the degree units, but in the circle units. So I start by 0. I go first in the positive direction, for example. I start by 0. And I look, what is cosinus of 0? What is sinus of 0? Well, we know what it is. It is just the coordinates of the point that is 0 on the circle. Well, we just look at the coordinates. Coordinates are already stated here. That's just 1, 0. And we see cosine 0 is 1. Okay, at point 0, we just have a 1. Okay, now, of course, there are some points that are kind of tricky. Right? Of course, I could draw now pi divided by 6, because we had that in the previous lesson, right? In the previous trigonometric lesson, we had pi divided by 6, and I think cosinus, oh, actually I know, I think I know. Okay, so here we have 3, right? And we know that pi is around 314, and if that would be 4, then pi would be somewhat around here. And pay attention, pi is 314 now as a number, but pi is actually 314 in sense of the angle, being considered as a number. Remember, we have circular units, and we consider measurement in circular units as simply numbers. So pi is number 314, but simultaneously it's the angle pi. No problem with that. It means that the angle, just like 0, we consider it is an angle, but we consider it as a number, right? Now pi is 314. No problem with that. 2 pi is what as a number? Well, 628. And of course, not 314, but approximately 314. But you understand what I mean. Of course, it's 3142 or something. I don't know it by heart, but yeah, you understand what I mean. So the angles are numbers, as we said. And that way we continue. So 314, or also pi, approximately 314, of course, but for us that is approximately pi. Then we have pi divided by 6. Well, let me just do okay, there are too many vertical lines now. Okay, let me say that this is approximately pi third. Of course, not quite neatly drawn, but let's say that is pi divided by 6, right? And now the value at this point, well, the value at this point, we know what was cosinus of pi divided by 6. It was square root of 3 divided by 2, right? If you don't know it anymore, then look up in the previous lesson. And of course, there is no contradiction to our approach that here we looked at the coordinates of this point. We can also determine for angles under 90 degrees and also by symmetry for other angles. For example, pi p6 here, I could also know that because it's just pi 6 gone from here, right? Same thing, so I could immediately know the cosinus of this if I know cosinus of this. We could also approach for the angles lesser than 90 degrees this problem from the right angled triangle, because this cosinus and sinus values are defined, as you remember, so that they actually extend the usual cosinus and sinus defined customarily for the right angled triangle. So there's no contradiction in that now I'm talking about what we did in the last lesson, defining that or determining that out of the right angled triangle, the result should be the same. I could also measure the coordinates of this point. Of course, it would be difficult to measure that. So better not measure, but just consider this line, and we determine then the coordinates of the intersection point, and we would have determined such coordinates like here. And just the same would come out. So there are two ways to determine cosinus and sinus, or at least two. There could be multiple ways, but this is also another way that I use here because we have determined it out of the right angle triangle, so I don't use other ways. So here from the point, because it's immediately seen, here from right angle triangle. All right. So where were we? Right, the spiral and how we can read the angles of different layers of the unit circles, so to speak, from it. And then we tried to graph the cosinus, right? And well, first we have determined this, and we just positioned ourselves at the point 0, so the argument is 0. And now we consider the value of cosinus at this point, and this value is simply seen from the coordinate immediately. And now I talked about the possibility to determine the value, since it's the same cosinus is the coordinate, and also same cosinus for angles under the 90 degrees. Um, So we have two possibilities to determine the cosinus value on corresponding in corresponding angle points, and for corresponding angle values on the x-axis. And we now use our considerations from the last time where we considered that triangle with the angle, well, pi divided by 6 is exactly, huh? What's that? Well, that's weird. What? So, exactly. Well, where is the option to... Ah, right here. Right. And now we wanted to graph this point, and here we have, as I said, the angle. Wait, it wasn't here. Okay. So, oh, that's approximately pi divided here. You were here. All right. That's pi divided by 6, and we have seen last time what the cosinus of this angle of 30 degrees is, right? And the point here is square root of 3 by 2 and 1/2. If you don't recall that, just look at considerations from the last time when we dealt with trigonometry, and there it is computed right. And now we take this cosinus and we just look where it is. Well, that is of course here and here. So the cosinus goes down to, that's 4/2. That's 1/4. Right. Oh, well, right, that's 2/2. All right, and that's, no, sorry, 1/2. Exactly. All right, and that is above that, right? Actually this, all right, and this is then between 1/2 and 1. So here we had the value 1 and 0. Here we have the value between this, and this is bigger than 1/2, then this is approximately here somewhere, right? And you also see that it corresponds to this, that is just the coordinates, and coordinate is decreasing, so the coordinate is decreasing, so we go downwards, right? Now that's at pi 6, right? So that is approximately here. We are above 1/2 here, but we are below 1. Right, and that was wrong. All right, and now we go to pi third, and by pi third those are switched, right? Because we just have same, we just go from here somehow. If you imagine that you turn your page so that you kind of go from this direction and you go from this direction, you'll see the symmetry of the lengths of this coordinates, right? So this here, the coordinates will be switched, and the point with these coordinates will be then 1/2 square root of 3 divided by 2. All right, and that would be 1/2, right? Would be 1/2. Okay, then we have that. That is pi third. That is pi third. That is 2 pi third. That is 3 pi third. So next we have the value. Well, the value we want to take next is pi half, and you see the coordinates here immediately. That's just 1, 0. And here I deduced the coordinates knowing that it is cosinus and sinus, and knowing those coordinates, well, actually just knowing those coordinates, I just looked at those line segments, and I looked at those line segments, and I just saw that they are interchanged here, because here we go same distance, we go here, and here we had full, here we had full, and here we go by the same arc length on the circle from here and from here, right? Okay, interchanged, and then we are here, and here the coordinates are just 0, 1. So the cosinus of this is what? 0. Right, so at pi half, we just have 0. Right, and you see here we are in the negative part, right? And you remember cosinus is x coordinate, what we have used now the whole time. So we go here in the negative, right? Here, of course, point symmetric to this, so the coordinates are minus 1/2 square root, and that is now well, what's that? No, that's pi third, right? That's pi 6, right? And here we have to take pi third. All right, pi third, and here we will have 5p6. All right, pi third minus 1/2 here cosinus, because we have that point here, right? So we go symmetrically. That is here pi here approximately is pi half, and here cosinus is 0. Right, then we go symmetrically into the minus. You see cosinus is decreasing because we go in this direction, and this is the x coordinate, the cosinus, right? So that is now pi third. This is 4 pi third, right? Pi third. This is okay. What am I talking about? This is 2 pi third. 2 pi third, pi third, 2 pi third, 2 pi third, pi half. This is 2 pi third, exactly. 2 pi third gives you, well, same coordinates as here, but in reverse and with, not even in reverse, but with minus here, so minus 1/2, because we go same arc length from here, from here. All right, minus 1/2. Minus 1/2 is approximately, okay, let's draw 1 first. Minus 1/2 is approximately here. Right, so now we have what? Here we have pi, here we have that thing, and here we have that coordinate. You see it just goes symmetric. That's 5 pi 6, and that's 6 pi 6, so pi, and by pi we have just minus 1, because you see the coordinate is just minus 1 0. Minus 1 0. So what we have is kind of, looks kind of like this in my course it's not quite right, but so I'm not good drawer. Okay, so, and you see that pi, so that's actually something like that, but well, not quite. Well, you can draw it better, or actually the main idea was to show you how you draw it, and not really to draw it nicely, right? So here, of course, we go symmetrically, and let's draw it nicely. You have seen how it is drawn, right? We go same way on the whole circle here, and you see the points that I have chosen, they are symmetric, and actually with those points you can draw a nice graph. And I didn't do that, but you can do that. Like, you now understand the principle, that is what matters. And now let's draw a nice picture, well, more or less nice. We start here, and we go to pi half, and then we go to pi, right? And then we go here, just like that. Maybe it's a little bit too elongated, this plateau. It's absolutely too elongated. It's not what cosinus looks like. It's more like this. pretty right, right. And you see that since the coordinates of a point, here we have like here we have like pi, I mean here we have like minus pi. Maybe it's not symmetric. I have drawn it not symmetrical, but of course it is symmetric because you see when you go in this direction, and as I said, the coordinates that we take of the points, they are the same. And we have to go into this direction to draw the negative points, right? So we just have to trace out everything that was here. I probably should finish that because here here is something like 2 pi, right? 2 pi, we finish one circle into the positive direction, right? And that is what results, right? And you see here, we have gone to pi. I have tried to illustrate it here, right? And now we go same, but you see it is just the cosinus is here increasing, so it is negative, but the absolute value of the negative point is increasing, and you see it is symmetric in coordinates because it's just going same arc length from the x-axis. So from the symmetry of the picture, we see that coordinates are the same, but just with our sign, right? With the sign here being negative because cosinus is negative, but here it goes in this direction, so it goes exactly from there, increasing in exactly the same shape of the curve, right? I have drawn just a few points, but actually all of those points are having their cosinus peaked here on this axis, and then we draw point, and so on. So here the how the curve goes should be exactly the same, and it goes to 2 pi, exactly same, exactly copying what happened here, but corresponding to how the numbers now change in the opposite direction. So here we went like that, downwards, I mean downwards on the y-axis here, the values, we take value on x-axis, value on y-axis, so we go with x, with y, downwards, attaining the shape, and here we do the same, attaining a symmetrical shape with symmetry with respect to this axis, exactly according to how we would go with circle and look at those coordinate values with respect to x-axis now, because we are drawing cosinus, right? All right, and now look at the negative. As I said, points are exactly the same no matter which one of the circles of the spiral we take, and hence the coordinates are exactly the same. And so, of course, what is happening here is exactly a copy of what is happening there, only that it is all going into the other direction on the x-axis, right? And so it goes, you see? I told you that the circles go further and further and further. They go infinitely far. They never cease. They go into the negative and positive direction. 2 pi, 20 pi, 100 pi. They go. Now I have drawn it in negative. Now, so minus 200 pi or something. And here it goes in positive. And so it goes, right? So it's and the this copies itself, of course, it's 2 pi periodic simply because by 2 pi we begin anew, and by minus 2 pi same we begin anew just because we are moving on the circle and we are tracking same points, hence having same x coordinate, and here x coordinates of the points we have drawn here. Don't be confused that we take x coordinates here and here we actually using them as y coordinate. That's not how you should think about it. You should think about it as here we are having a mathematical construction, and this mathematical construction gives those and those objects, namely points with their coordinates. They are now the focus of our attention. And here we have another mathematical construction. And for this mathematical construction, we take from this construction exactly those parts from those points. That is how you should think about it. Not think about, well, that is x, and that is x here, and that is x here, so it should be on the x-axis. No, not like that. That's why I called that x prime and that y prime. You should think of mathematical objects and what we'd like to take from them, what we'd like to look at in them, and now what we would like to use in them and how, and not on some in itself meaningless variable names or object names. No, object names is how we refer to them. That's not objects, and that's not the structural relationships between them. They can only signify the structural relationships, but the idea is to think of structural relationships. And here the structural relationship is we take points, we take their first coordinate. Their first coordinate is what we take to be the value corresponding to our angle given on the x-axis. And angle is, of course, in our circle unit, right? So that's how you should think of that. If you didn't get that, then listen to this line a few times more and think about what I'm trying to do that here, what I'm trying to draw, and why does that make sense? What am I trying to achieve? Why does that look like that? And so, and try to repeat that best. Okay, then that is now why we could also say y is cosinus of x. So angle on the x-axis, or whatever I could call this axis, I don't know, alpha, beta, gamma, something. I could call this axis ABC if I like. Of course, it's not customarily, but I could call this axis ABC. I could give it this name. Then that would be cosinus ABC. It doesn't matter. What matters is structural relationship. And here we have the angle from our circle. And here, corresponding to this angle, we have the x coordinates of the points which we consider on this circle. And this circle is just a separate object from which we take those points and give them to the angle in sense that we give the points on the x-axis that correspond to those angles. I mean, we give the coordinates on the x-axis that correspond now to this angular coordinate in the circle. We give them exactly the y value which we choose equal to the x coordinate now in this mathematical structure. We choose it as x coordinate of the points corresponding in this mathematical structure to the respective angles, right? It might seem too much, but it is not. It just seems too much because it is too much at once. You just have to reflect about it and to kind of get it out of this woo knot. You have to unknot it. You have to unknot all the different connections that I have now put together in my sentences. They're clearly put together, but you have to realize them one by one the first time before you get accustomed to this thinking. If it was any challenge for you. Because, of course, there are people who would get that immediately. Not necessarily everyone, but yeah. Okay. Right. But for some people, it might be difficult. So I'm spelling it out very explicitly. Okay, here of course 1. Here we have zeros, clear. Here we have of course -1. Yeah, and so it goes. So now you could actually draw those graphs yourself. But now sinus, what do? We do same things, but the coordinates that we now take are y coordinates from this structure, right? Take an angle on the circle, take the point in this structure corresponding to this angle, take the y coordinate of this point, draw this y coordinate here corresponding to the angle taken here. You could also imagine that I'm just flattening here out my circle with x-axis, but the y-axis I just take as some abstract y-axis, and I just take this coordinate there. You do not need to conflate those pictures, but if it is easier for you, just imagine this is just my axis as a spiral, spiraled around this here, right? This is another construction thought or made up by me now. You don't need to think in this construction. It is just for to properly connect for you this x-axis with this circle, right? And here also this x-axis with the circle. This is always actually this kind of this circle. But you don't need to think of these words precisely. It's just one way to put it. There are infinite ways to put it. This is just one way. And if it confuses you, then forget it and think of the previous stuff. Because the stuff that is important is what we are doing, not how we phrase it. We could phrase it in multiple ways, as I said. All right, now sinus. What do we have here? Well, you can follow it up on the circle, but I will now do it quickly. We have 0 here, the 0 coordinate, 0 angle on the circle. We go now further on the circle. We have pi6, and pi6 now has this coordinates, and we take the y coordinate, that is y 1/2, and pi6 is approximately here, and that's y 1/2. Now we have this other thing here. Yes, that was 1/2 here, and now we have this other thing here, and now we have the other thing, symmetric. So this is one square root of 3, and this is at pi third, so 2 pi 6 at pi third, approximately here. And now we have 1/2 again at what? Well, here we had pi divided by 6. Here we have 3 pi divided by 6. So here we would have pi divided by 6, 3 pi divided by 6. Here we would have 4 pi divided by 6 somewhere here. Oh, no. Pi 6, 3 pi divided by 6. What am I doing? Yes, 4 pi divided by 6, or 2 pi third would be exactly here. Then 5 pi divided by 6, and that would be that. Then we would have, of course, pi half. Pi half would be that's pi 6, and we would have 3 pi 6, so that's exactly here. And now we would have 1/2. 1/2 would be approximately, oh, sorry, not 1/2, we would have 1, and that I said was that, and then 1 would be here, right? 1 would be here, Now we would have here 2 pi third. Now we would have here whatever 1/2. I mean 1/2 now the y value, right? And now we would have here the value of pi, and here we have 0 again. Right, so pi here 5 pi 6. Here we would have 2 pi third, here pi half, here pi third, here pi 6. Right, that we have here. And of course it continues just like that into the positive and negative. Well, not just like that, wait a minute. I mean just like that in the sense that we recover our values on the y-axis in exactly the same way. Here it continues like that, and here we are done with our period, that is 2 pi. So we begin our sinus journey in the positive. So here when so here we have arrived. You can follow it through by particular points using symmetries, as we said, using the special values of the points that we have recovered in geometric way, and so on, right? And here it begins in U, of course, and so we have to repeat it just like we had to repeat it here, right? So even if it is drawn a little bit differently, it's supposed to be exactly the same as here. You probably have seen those pictures already, right? Because, well, you can see that it is the same because it's coordinates of same points that are winding up there, right? Right. I mean, one coordinate, but coordinates in sense that one coordinates. Y coordinates here, x coordinates here, but y coordinates as x coordinates. Remember that in reference to this structure, right? All right. All right. And then it just continues, right? Our circles that we will have here. And that is, of course, 3 pi half. This is minus pi half. This is minus pi. And so it goes. And you already see here, of course, it's no trouble to see it from unit circles, just how it works, how the spiral works, because the points are set to repeat from there on, and since their coordinates repeat. It's just how these functions are defined. They are 2 pi periodic. But what does that mean, 2 pi periodic? Well, we see it very nicely here. That repeats, that repeats, that repeats every 2 pi's. But how do you write it mathematically? Well, sinus and cosinus functions are 2 pi periodic. For that, we have to write in mathematical notation that their values repeat, right? And we have seen that we denote the values somehow from one variable. We call that variable x, and we call the y variable, and we call the other variable y. So if my function is y with the argument x, right? I should write it properly, neatly. My function is y with the argument x, and that is cos x, right? Y of x is cos x, right? Then how do I write that the values are the same after 2 pi? Well, I have gone to pi on this axis, and there I should have the same, or it should be all the same if I stay here at 0, for example, when my value is something, for example 1, but doesn't matter what exactly it is, my value is something, I go on to 2 pi, my value should be the same. That is, I evaluate that first at x, y of x here, my x is now 0. Then I go on to 2 pi, that is to 0 plus 2 pi, or generally to x plus 2 pi. That was here for the x's, right? Then my value y should stay the same, which I have written there, here. Y of x plus 2 pi, so y at the point x plus 2 pi should be same as y at x. And now, no matter what x I take, okay, that's not written nicely, but yeah, not drawn nicely, but yeah, that's what is meant. Right. So y of x plus 2 pi, we go to pi step until here. We go a big step in the size of 2 pi. And here the value should be the same. And so it repeats, and the short form is that here. And that is true for x and for cosinus and for sinus. And since our y is now sinus and cosinus, we just write cosinus x. Now cosinus is the function, right? And actually it is quite more suggestive to write it here, because it's just, well, that is our angle, right? That is our angle alpha. Recall what it was. So it's exactly that cosinus that we have here. There's no difference in values for the angles taken on this axis from the cosinus taken in values of the angles on the circle, that is in the x coordinates here. You see? And I should not actually tell you that the models are the same. It is just not the same, but that the models same this thing. In mathematics, it is just there. It is just what everyone understands automatically, right? So think about it, what that means, because, well, there are some people who just think if there is some, I don't know, something is called something, and when I square this, that this might be something else. Of course, they don't think it in same context. In a simple context, they think it in a more complex context. But like, you should understand where something is the same, where it is not. Of course, I know here I write x, and here I write, okay, here I actually wrote x prime, what we used for the functions. But okay, here I could have written x, here I could have written x. Is it the same or not the same? Well, there you should pay attention to the context, because it's a customary practice, at least in serious mathematics. Well, if you are a neat person, you will use different notation in different places, but oftentimes it just becomes too much and you begin to use same variables some in some different contexts. That is just how it works, right? And then it is important what this variable actually means. All right. So keep attention. The same is not the same, and sometimes is the same still the same. So the important thing is the mathematical interrelations. Right. Cosinus of x plus 2 pi is cosinus x. And this is what we see here. And here you see the whole picture, and you just think how I told you it works. And then you will see, is it supposed to be the same, or is it not supposed to be the same? If something doesn't make sense, then it might be my mistake, or mistake of other lecture. What do I know? I mean, if you are hearing other lectures, but it will be seldom the case when the mistake would throw everything off. Of course, it can happen. No one is infallible. But usually, if everything doesn't make sense, If nothing makes sense because of this mistake, usually the mistake will be on your part. You didn't internalize the things properly. I mean, not internalize in sense you just memorize them without understanding. No, I mean you haven't pierced them with your mind properly. And if you pierce them with your mind properly, then you understand why it is no mistake but the right thing. But of course, we all make mistakes. That is absolutely granted. But well, usually you have to think twice and about the whole structure. Right. In these videos I already made some things that were wrong. I mean, not necessarily mathematically wrong, but just written wrong index or something. Those mistakes are common. But mistakes like conceptual mistakes, where a part of a model, uh, an important part, just isn't working with our parts. This is really problematic. And that would be seldom, maybe even really seldom. Right, maybe even never, but well, who knows? I have found such mistakes sometimes. I mean, not, oh, I mean, in some lectures, but okay. Not by me, I'm talking about me. Okay, so that was a short reflection on how important it is to think of mathematical structures and not just of symbols, not just of how something is named, but actually how it works. Right. And for sinus, we have the same, of course, right? We have just seen its same pattern of the behavior. We have that. Sorry. That would be really a crucial mistake. Of course, it would be a typo, right? But if I would have left it here, then it would be just plainly wrong. Of course, I said sinus exhibits the same pattern, and hence we get that. All right. And again, here we map our angle, and here we have corresponding sinus, which we can lead up nicely from the circle. Right. Okay. This was the sinus and cosinus story. Now, of course, same way we could graph the tangent. For the tangent, we would take the unit circle again. We're always taking unit circle. This is, by the way, important, just customary. The sinus and cosinus functions are always taken for unit circle. And you understand what would happen if we would take it for a circle with other radius. Right? It would just be scaled. They would just be scaled. But the behavior of the functions would stay the same, of course. Of course, if we would take the period, this is, by the way, is called 2 pi periodic, 2 pi periodicity, because it's like the whole period, and after this period it begins new. Kind of like by period you could think of the mathematical this thing that is hanging there and going there, there. The period is in here to here. I mean, both from here to here is one period because we started here, and from here the motion goes the same. But of course, I mean by the mathematical pendulum, it's called, and that's why, or you could think of that's why it's called period. Of course, by mathematical pendulum, where you don't have any gravity, it just constantly goes there and there with same velocity, no friction in the air, it just goes same way. And this is one period. This. And not this, but this. All right. All right. Tangent, we could draw the same. Of course, here we would have some undefined tangent because we would have that cosinus is actually 0, right? Cosinus not of 0, but cosinus is equal to 0. Because you see, again, I'm using the coordinate cosinus pi half is equal to 0, and we would take the tangent. Well, you remember tangent is just the fraction, and here we would have 1 divided by 0. Of course, it doesn't work, so here the tangent is not defined. And well, here the contrary, I mean, here it is defined tangent. Okay, I could write it tangent pi half. Here sinus of what? Of 0, cosinus of 0. Well, cosinus of 0, remember the x coordinate is 1. Here sinus of 0, well, the y coordinate is here 0. So there's a 0, and that is tangent of 0. And so you go the whole circle again and again. You have this spiral. So for all trigonometric functions, always have this spiral of infinitely many circles, but geometrically you take same points. It's just convention. So geometrically you kind of project the spiral on same circle, right? To take the corresponding points. The corresponding points are taken from the projection on this circle that is in the plane, but the spiral goes in 3 dimensions above all that. Right, that's for the spiral. Right. All right, by the tangent, the same, it goes like that, and if you would draw it out, I wouldn't do it so precisely. You could do that, of course, like, okay, you take the angle, now the angle is 0. Now you take like by half, we would have some problems, like it is not defined here, right? And I already tell you that it is an asymptote, and well, you can think of it. It is easily seen that it has to go actually like this. This, you see that because you see here, if you look at the coordinates, we have already seen it here actually on the graphs, because in the graphs you can see it neatly, right? Here the cosinus increases as we go like that because the x coordinate decreases, right? Cosinus is x coordinate, right? Here it goes like that, like that. And sinus increases because it's y coordinate increases here, so yeah. All right, so the numerator would increase, as we said, sinus increases, denominator would decrease, and so it goes, of course, off to infinity. And by, I don't know, by fourth, if you recall, by fourth, the corresponding coordinates were, I mean, of sinus, cosinus, that, and if we are equal, then the tangent is just 1, and that we could draw out here. Well, if I'm taking here pi half, right here I'm taking pi, and the 1 would be approximately something like that, right, and 1 would be here, like that is pi fourth. And here you would go off to infinity, as I said, right? So the tangent would go something like that, right? And here, of course, symmetric, but in the other direction, just in the same way. This tangent just takes the coordinates, but the coordinates are same but symmetrically just same, except for the symmetry with respect to x-axis, that is the coordinates of the points. The points would just be taken with minus, and so the tangent goes with same shape, but goes with minus, and goes, of course, in this direction. So what we obtain is something like that, and here, of course, minus 1 or something, and that goes off to minus infinity in the same way, and here's minus pi. Okay. I have shown it wrongly. I have gone uh, further in positive direction, but of course now I'm going from negative direction, and what is happening is just the same, because here again symmetry argument stays the same. Now we go here, now we are here, points are the same, coordinates are points are the same except for minuses, coordinates are then the same except for minuses, and then we get um, that, and pay attention, minus only is applied here to the y coordinate, but x coordinate stays exactly the same. That is why negative divided by positive, we go into the negative, and shape is the same because we are symmetrical. So we are symmetric on the circle. All right, in the values. In values, and only signs changes. Signs change. Right, and this is an asymptote. All right, and as you can think, that will repeat, because here we have just something in the negative, right? And here we are, of course, rising, we are in the negative, and we are decreasing in sign, and we are increasing in the negative value. We are decreasing in positive sign, and we are here decreasing in the negative value, so that what we obtain is actually decreasing in the denominator, and it is decreasing in the numerator. Well, and so we actually should what I'm not getting now, that is by half. No, yeah, that's by half. That's pi. And we have our cosinus that decreases, and we have sinus that decreases. Right. And here again, only one sign is swapped. Here one sign was swapped. Here only one sign is swapped. And the values of the respective points, well, they are the same because of symmetry. Only their signs are swapped. Generally, if we are on the unit circle, if we take that and we take that, and we take that, and we take that, and we compare the coordinates of respective points here. If we go throw points here, throw points here, I mean in the quarter of the circle, throw points here, throw points here, and of course here we would have points with certain coordinates. Here we would, if we go through points, have exactly in total points with same coordinates, but with the uh, x coordinates swapped to minus, right, in total, because it's symmetry, right? Here we would have exactly same points here in total, but with both coordinates swapped to minus, and here we would have the x coordinate plus, and the y coordinates swapped to minus, but it would be same points. So be aware of the symmetries and how they are reflected in coordinates. Right, so here would be then another asymptote, and we are in the negative, but the shape is the same as here because the coordinates are same except for where we have the other sign, but we have just quotient, so the other sign goes to the quotient, just like here the other sign, I mean minus, goes to the quotient. right? And here then the same, and so it goes. So tangent also has some periodicity. Of course, that is now minus pi half, or if we go into the positive, recall positive goes like that, pi here, here, plus pi half, 3 pi half. Right, and it goes like that, and here, of course, what goes here? Okay, again, you have that, and here we have now gone, here's 2 pi through the whole circle, and here the gain begins again just because of 2 pi. But you see, the tangent is repeating more frequently than just 2 pi. You could say that its period is 2 pi, yes, but you could also see that it is not the minimal periodicity of the tangent. The minimal periodicity is just pi, right? Because if we move pi on this axis, the values repeat, right? So tangent is pi periodic. Right, and here we have what? Well, that was minus pi half, and that is pi, and that is minus pi, of course, we go into negative, 3 pi half, and so on. And so it goes, right? So of course, I don't have to draw it like that. I can draw it properly. Right, it doesn't touch it, right? It doesn't touch it because at this point we don't have any value. You just drawn badly. And that's the tangent, right? And we said that tangent is pi periodic. What does it mean? Well, tangent x plus pi is equal to tangent. And same, you could draw for cotangent and whatever trigonometric functions you have in mind. Oh, maybe not whatever functions, but for cotangent you could draw it. All right. I'm not doing it. Right. And next up, we'd like to consider the inverse trigonometric functions. I don't know if it is still a topic at school, but um, I'm painfully aware of how well, let's say of how bad it seems to be with the understanding of the inverse function, at least in some cases of students. And especially of inverse trigonometric functions. It's like, yeah, I I won't talk about it. Okay, so let's consider inverse trigonometric functions. Solve the mystery. What is that? Well, it's actually very simple. You see? What is the goal of an inverse function? Well, just imagine you have something like it's just you know, it's just a collection of points in some I don't know what in some set actually, but you probably don't know the notion of a set. So let's think of it just as of where the collection is in. This is just some container for this collection, right? If we have 5 and 5, well, you know probably that something like that is not considered a function. That is, if we want to assign to a thing two things, it doesn't work, or more than two. It just doesn't work. It's not a function. Of course, it works for some mathematical objects, of course, your generalizations and things like that, but it's not a function. A function is defined so that this is impossible, and so that everyone gets something. Right? This point can't get more than 1 point. That's impossible. But everyone gets something. And it could get same point. But important is 1 point doesn't get too many points. And that is too many. More than 1 is already too many. And whatever, it could be like that or whatever. As long as I satisfy this requirement that from 1 point there are no 2 arrows to 2 different points, that's okay. And by arrows, I mean assignment. That is, I take this point, I assign to it that, and that is a function. That is actually what a function is. If we also take the requirement, this is only that is deleted, that is still there. If the function satisfies those 2 requirements, that a point gets a point, every point gets a point, right? The point in chosen set called the domain of the function gets a point, and no point gets more than 1 point, right? And gets goes in this direction. We consider these points as the starters, so to speak, and those are the ends. All right. Now, of course, an especially nice situation is given when one gets 1 and everyone gets a different one, and there is enough for everyone. And this is especially a nice situation. What are unnice situations but still functions? Well, here we have 5, here we have only 4. And so if we want to satisfy the requirements for a function, or we could also draw this to one of those points that is an alternative for this, or could also be alternative. And it will be a necessity, just think about it, that one of the points is met 2 times, right? And this is not so nice. See, here we could just take a point here and we could immediately know, oh, what point was this point assigned to? What point was this point? We now want to start here. This was what point was this point taken here? Not starter points, but taken the assigned point. What point was this point assigned to? Oh, we know it exactly because there is only one path. The one path that went towards this point. But here, let's say we are here. And let's say this alternative was not taken. We are at this point. What point was this point assigned to? Oh, might be this, might be... Actually both. Actually both. So there is no single defined point to which this was assigned. But here, nice, we can go back, right? And here we now take the alternative, so this is deleted, otherwise not a function, right? And this we take, and then again, from this point. All right. Why is it not nice? Why am I calling that nice? That you'll see in a second. Now, another situation. Here you have 4, here you have 3. No. Here you have 5. And you know the requirement of a function, we can only cover 1 by 1. By 1, we can only cover 1 as a sign point. But 1 remains here. No problem. Function requirement is satisfied because no one got more than 1, right? And also everyone got something. But this one is lonely. So there's nothing for it. It can't. If we stand here, we can't go back. It's just bad. Right. And why is that nice in this situation? Because if we wanted to go back, you're welcome. You can go. Just stay here. Just stand here, and you just have to follow this arrow back. You stayed here, and that forget that for a second. Just stand here. Oh, I can follow back. And here I can because I could go back to there or to there. Don't know which path to take. But here, oh, only one path. Oh, only one path. Oh, only one path. Oh, only one path. And this going back is called inverting the function. You see, here the function went to there, and the starters were this point. But now we can invert it if it is especially nice. That is, to everyone belongs exactly one, and once something is taken, it can't be taken another time. Don't confuse that with the requirement of a function. That is just that one can't take two. That's not that. This is different. This is here two take one, and two can take one theoretically, but especially nice is when they don't, because then we can go back. And that is inverting function. But of course, you can think already that we are not satisfied with starter sets or starter collections where we just have a finite number of points. We are not satisfied with that. We are actually interested in functions that go from whole intervals or from whole real line, right? Because that's the usual case. Oh, let's think about it. How could we figure out what functions would be especially nice in this case? Well, let's see. Take this function. This is just some f of x is equal ax. You know this function? That's just a line, right? With the slope a. So the tangent of alpha is a. You can recall tangent, and you can just think of here a triangle, and you can just think about that. That is a. All right. And now I claim that this function is a nice one. Why is that? No, that's simple. Of course, it is a function. It is a function just because 1x has exactly 1 point. We go above and we go here. But now, you see, we'd like to have also this, that 1 takes 1 and it is taken. How does this work here? Well, that is this y value should be taken. And we just trace for all y values of this function. Oh, nowhere, because this function goes to there and to there. Nowhere this y value will be taken another time at no x at all, right? And this is the case for every y value. So this is a function, as you know, and as you can see, and this is a nice function because no y value is taken 2 times. Remember, here the points there are just the points x, I mean the points on the x-axis, or the places at the x-axis, or the numbers at the x-axis, and the numbers at y-axis. So we have consider exactly this requirement 1 to 1, but for sets that have more than finitely many elements, or for collections that have more than finitely many elements. So it works, right? And it works because we have this graphical image of the function. And this is exactly what it depicts. It depicts the points x, y, right? So we can kind of check visually whether for same y there are different x's. And for that, we just go and trace all y, because if there would be a y, then it would be taken as a point here. And for example, if I would give another function, that would be g of x equal x squared, and I don't care how I have drawn it. You understand that I don't care. 2 points. That's a problem. As soon as we have encountered that, bad function. Doesn't work. Right. Even if it would be something like, oh, I don't even know, something like this. Okay, no, forget it. You probably are not interested in complicated functions, so we don't care about it. Okay, so this is a bad function in that regard. But let's take a half of it. We just forget this half. We just consider this function only on this. And then it's a good function again, right? You can check by this requirement. And of course, you can actually see directly that this works after you have understood how you check if your function is good. So what does good actually mean, and what is it called mathematically? The function is invertible. The function is invertible, and that is very nice. That is totally nice. And what is the same as invertible, but is defined differently, is bijective. But just care about invertible. We don't need to go into the detail here. Right. Okay. Now, these functions are not nice, right? They are somehow go like that. I mean, not nice in this sense. So here they are even the worst because they are periodic. That is, their values will repeat forever and ever. Will repeat completely. So there will be infinitely many values and more than infinitely many that are repeating for different x's. Y values will repeat. Of course, we see that they must repeat because they are unreversible. But nonetheless, you see, your calculator somehow is able to take inverse functions because of that. I don't know what notation you prefer or what notation you are familiar with. Arcos cosinus, arcos cosinus, or cosinus to the power of -1. These are the inverse functions. How does your calculator do that? He shouldn't be able to, because those functions are clearly not invertible. So am I telling you bullshit? What's wrong? The answer is they are not invertible if we take them at large. But now consider this one piece. Consider just this single piece. Looks nice, right? Looks invertible. And it is invertible. You see, if I take this single piece, only this, then this function looks totally invertible. And it is. So smart guys came up with the idea to invert exactly this piece, just like here. You probably recognize if that is x squared. What is the inverse operation to x squared? Of course, it's the square root, right? Square root x squared. Ux. But how it is connected to this calculation, invertibility, we will see in a second. Why suddenly assignment and inverse assignment has something to do with calculations? Funny, right? Right. So I'm not telling you bullshit. I'm just uncovering the bigger picture. All right. That is where we arrive now. And now let me tell you how those smart people actually found a way, in a way, to invert those things. They just take a small interval. If you can't invert, that is, function is not invertible, try to restrict the domain. Of course, there are sensible restrictions and unsensible restrictions, and in this sense, the restriction is very sensible and very nice. Exactly because the functions are periodic. So it threw off our general attempts at inverting because the functions was not good. But simultaneously, it will be good after we found a good place to invert. It will be good in the sense that we can nonetheless get hold of those places in a way where the function is not invertible by means of something that successes the inverting in our calculations of certain kind, but okay, we will get to it. If you can't invert it, try to restrict. And of course, by that we mean the domain. Right? So the x-axis as domain is just real numbers. It's just all numbers you have learned in school. It's just all numbers are called R. And the function cosinus, it goes just from R. We could take any angle. Remember the spiral. The spiral spirals to eternity from 0 in the positive and in the negative, goes to pi, 2 pi, 4 pi, and so on. And between those, all numbers are taken, just like here on the axis we go, right? All right, and it goes to R, of course, because, well, the values cosinus, sinus are certainly the elements of R. Of course, you could say, well, no, it does not. It goes to this here. And you would be completely right, because we don't take any other values, right? We stay in those borders. For cosinus as well as for sinus, we just stay in those borders. You would be completely right, and I'm also right. It goes to R because this is subset of R, right? Because this is included in R, right? So this is completely, all those numbers are contained in R, and that is called actually subset of set, which R is. But okay, that is completely included in R. All those numbers are contained in R, right? This is interval. If you don't recall, interval is this thing. That's just all numbers A for which we have that. And if you draw it on the number axis, you just have here -1, here 1, and I take those numbers, those two, and I take everything in between on the real axis, right? All numbers in between, right? All right, but you would be more right because I'm actually interested in going to there. Because, if I take this, then I'm destined, or it is pre-programmed, that I'll have lonely elements, that I'll have lonely numbers. Because, like, I'm staying between -1 and 1. So I must have 2. 2 will belong absolute. 2 won't have anything to go by, right? It will be this situation. We'll have 5 and here 4, but there we have infinity and infinity, but, well, the numbers won't suffice because the function is defined that way, that it repeats, right? Right. So, and that's why you are completely right and you have given a better definition, it should go like this. But now we said, no, if we take O, then it does not suffice to restrict our value space. That is the space where the values are taken, or the collection where the values are taken. No, it does not suffice, because we should also restrict here. And then I come and say, oh, yeah, you're right, actually. Let's restrict. Let's consider our function. And that exactly means cut this piece out. On here. And what is this? This is exactly what we wanted. This, we take only values from here and we assign to them their cosinus, which is exactly in this interval. And this exactly means we have taken out the piece of interest where the function is invertible. We have taken out this piece. You can now imagine that our axes now are here, the axis stops. The y-axis stops at -1, at 1 here, 1. Here it stops at -1. It doesn't go any further. Here we have that our x-axis stops at pi. And here we have nothing because our x-axis actually stops at 0. We have this restricted picture. And here our function goes. And now it has become nice and invertible, right? Because it just goes like that, right? We have just restricted. We haven't done anything else. That's why the shape of the function didn't change. Oh, okay, in my picture it has changed, but you understand. I just took this piece of cosinus. Of course, it doesn't look like that at all, but yeah. Okay, so that is restriction of cosinus. And well, write that here. Oh, you probably already hate my style. Sorry, of course, we didn't take this because we want this, and we take it from 0. So, of course, I meant this. We take it from 0 to pi, right? Because we want this piece. Right, and this is the restriction. And this is what we are interested in. And here we can invert. You see, the function is totally nice, right? We had to restrict the domain and we had to restrict the value space from the most obvious one which we could think of. Right. And this is what the smart people do, what your calculator does. It works with the restricted function. And for that, well, that is invertible. The function is very nice. And what does it do now? Well, you tell him, well, I give you an angle, but we'll get to what happens when we give him other angle. But let's say you give your calculator an angle from here, then it shouldn't have any problem. You give now an angle. No, sorry. Now, how your calculator works? Your calculator can actually go back, right? Go back from given cosinus. That is what we would like to do. Like here, right? We would give cosinus, we would go to angle back. Because the function itself, it took angle, it gave him cosinus. That is, we kind of had that. Angles, cosinuses. Right? That was just like here. Only that we had 5 pieces, right? Or 5 or 4 or something, finite number. And here some pieces were assigned to some pieces. But now angles, we take all angles as pieces. If we would have taken 5 angles, 5 somehow distinct angles, then we could have done same with the cosinuses, of course, but that's boring. And it doesn't bring us anywhere. It doesn't get us anywhere, right? That's why we take all angles, all cosinuses, and that's what we do here. But of course, in the restricted domain, 0 to pi. Right. And we just assign, well, just I can't draw here points for angles because it's infinitely many, you understand, so I don't do it. And here we have all cosinuses, but just imagine in here all angles are in it, all angles in this restricted domain. Of course, uh, I'm not repeating that because this is now what we consider, so keep your mind on that. Right, this restricted domain, all angles in the restricted domain, all cosinuses, and this is really all possible cosinuses, right? All right, and now your calculator must have an easy task if you give him like cosinus of some angle here, right? What does it do symbolically? Of course, it doesn't do that. It does approximation calculations. But what does it do symbolically? If we take some, that's not pi thirds. It's just any angle in 0 to pi, right? In this, if we look at this interval on this circle, it would be this from here to here, positive, right? It just goes and says, all right, he gave me that angle. That is with that angle on the cosinus axis, right? Not on the x-axis, but on the cosinus axis. He gave me that angle. I find that angle, and I can go back. I can go back to the coordinate of the. Oh, sorry. We are considering inverting, right? So we go back from cosinuses to angles. We go from angles to cosinuses by cosinus, but the calculator now has the opposite task. You gave him cosinus of some angle, but of some angle from this domain. And then it should have no trouble because it takes this cosinus, just finds the number of this cosinus on this axis, symbolically speaking. And it goes to this number. Of course, it's not, okay, let me draw it properly. It goes to this number and just tells, well, what angle is it? Okay, I look here. Of course, it's not what it does, but symbolically it does actually this. Right. In truth, it does approximation calculation using the Taylor expansion of the functions, or probably not Taylor, but some faster. But yeah, does expand them in some series, which allow computation. But what it does conceptually, symbolically, it does this. It takes this value, it goes to here, and it looks, oh, here, your angle. And it can do that for any value of cosinus as long as the angle you mean isn't here. Right? But what happens? Right? That just works. That just works. You give any cosinus, and if you think of an angle in this 0 to pi, then this function is invertible. We can go back anytime. It also looks invertible, so that's what I mean. And we can prove, of course, we can prove properly that this function is invertible. It's also actually very simple. But I won't give you the proof. It's far over the head for the school level because if I would want to give you the proof, then I would have to give you the formal proof, and for that we would need a lemma for which we would need really formal stuff to prove it. And well, that would be too much for you there. I'm not hypothesizing. I know that. And that I will do in my analysis, my calculus series. So if you want to know that, look up in calculus series because it's not for school level. Right, but inverse functions I want you to know, and I'll just give you those heuristics. So the function is invertible. We can prove it properly. And hence we can just define this function that does exactly that. What we just said, the calculator does. Or that's same as arc cosinus. That's arc. Actually means give me the arc length if you have the cosinus. That's why arc. Right. That's no problem. And those angles are called main values of the arc cosinus. Right? So if you give cosinus from here, then the arc cosinus will always be given in here. Right. So you give him a cosinus of alpha. And what does it give you? It gives you always alpha, but always alpha in 0 pi. So if you thought of such an angle, it computed the cosinus. Cosinus of alpha is, alpha in 0 pi. I computed cosinus, and I gave my calculator the task to compute the arc cosinus. That is, give me the corresponding coordinate here, right? The corresponding x coordinate. So it goes here and looks here, and gives you this angle. But you see, this angle will be always in 0 pi. Right? So if you computed some cosinus of alpha, and alpha is not in the interval 0 pi, and that can happen very easily, I could have taken just, I don't know, alpha from here. This alpha would be in, in many intervals, but for example, in interval of pi to pi, right? On the upper half, on the lower half of the circle. So here's pi, pi is excluded, and here's 2 pi somewhere, and the spiral goes further, right? Alpha would be just an angle here, right? And what would it do if you would compute the cosinus of that? As we said, the cosinus repeat because of the symmetry of coordinates of points on the unit circle. That is, if you give it an angle from here, it would not know that it is an angle from here, that you computed cosinus of such an angle, right? You computed actually that, right? But the calculator would not know that. The calculator would give you that angle, which it would get for this cosinus on here. And what angle would it be? Oh, of course, that angle whose corresponding point has this coordinate. But it would be always an angle in here. So in this case, if you have that cosinus, you can see very clearly what angle it will be. It will be this angle. So it's on you. It's on you. If you don't take the main value and you compute it, or if you have some calculation in some subject that is not necessarily mathematics, in some engineering subject, and you computed something, you computed some angle, right? Computed some angle, then it is on you to know, is this angle in here or in here? If you don't know that for some reason, then you would not be able to distinguish. But the arc cosinus, or the inverse of cosinus, would always think that you took an angle from here, and it will give you an angle corresponding to the cosinus you have from here. And you could now take angle from another windings of the spiral, right? You could take, I don't know, 13 pi divided by 2 or something. Of course, we could. Okay, you could take that. And again, it would go back to the principal values and would give you, you computed cosinus of that or something. And it would give you again this thing. And if you don't know that, if you haven't learned that at school, and you are confronted with this task, and you just don't know that the arccosinus always gives you the angle in principal value. Then computing this, you would have computed cosinus and some, I don't know, some calculation that gave you cosinus of some, I don't know, some two details of some angle which you have to uh, put together. Then this, I mean, this and this would be indistinguishable for you. Of course, you could rotate it, but imagine now this is fixed, and you'd simply computed the cosinus of that angle. I'm now kind of here, right? And that would be that here would be cosinus, and here you would have the same cosinus, right? And you now have computed the cosinus, and you took this angle. This is now fixed, and you now computed the cosinus from some crazy calculation. And now you want to determine the angle using the arccosinus. You don't know if it is this angle. You are not even thinking about this angle. You just take this. And your chief comes and asks you, what's that? What's that? Right? You understand the situation, right? He wanted that. But you only computed cosinus, and then you computed arccosinus, and then you computed the angle. But the stupid calculator didn't know that your angle actually was supposed to go there. And so you take this angle. So you have to think. You have to think. You should not think that arccosinus somehow knows what angle you meant. No, it does not, especially in mathematics. That was rather a harmless example. If you don't know how it works in mathematics, then you have real trouble. I mean, it is real trouble too, but I mean, here you could, yeah. Okay. This is inverse function of cosinus. And this is how it works. And now, if you knew that it is this, if you knew that you actually wanted, that you just knew from construction, you have read the construction papers, you know that it is this angle actually, you have taken a look at blueprints and you understand that it is not right to simply take this angle and to attach this here, then you have seen that it is actually this angle. Right? I mean, you measure the angle from here, so don't tell me you took this. No, you are smart enough to measure the angle from here, but you are not smart enough to know. You have not learned that the arccosinus is and how it works. So you you end up with this. So yeah. And now imagine you knew that, and then you measure the angle from here, and you ended up with that. But then you know the arccosinus give you that. But then you just know how you switch to there. And for that, you see the arccosinus works like this. It works like this, right? But those angles are just symmetric to that, right? So you could take the negative angle if you like. That would be exactly going from here, right? Negative angle, right? Going from here. Or you could take, if you like, to stay in the positive. Well, how do we come to this point exactly in the arc length? Well, we take 2 pi. And then we take this piece minus from here because we have to go back like this. And you have 2 pi minus alpha. So if you have something like there, like here, and that gave you alpha, Then you just take from the stupid calculator, you just take his arccosinus of some, I don't know, cosinus of alpha. And now if that gave you angle, right? Because arccosinus takes cosinus. Don't be confused by that. Just see it one element by one element. You computed some cosinus of your alpha from some crazy calculations, and your stupid calculator gave you alpha as this, right? Arccosinus give you alpha as this in this interval, right? And now you know, but that your angle actually is larger than 180 degrees, measured from here. And then you just know, well, I have to go here because you imagined the unit circle and you looked here. And then you just know you have to take 2 pi minus what this stupid calculator computed. So this is how inverse trigonometric functions work. Of course, for sinus, you do the same. By the way, one another interesting thing. But you could tell me, don't like this. I don't like the first one. I never liked 0. I want this one. And you are right. You could invert it there. You could invert it there. It's exactly the same piece. You know about periodicity, right? You could draw your x's. You could invert it here, right? No problem with that. But all the stupid calculators are tuned to work with same main values and to agree that it's just a good practice because, well, if we would be all tuned to work with the values that your constructors liked best, then we wouldn't have the compatibility, right? So would be a problem. Now we go to sinus, and here again you have to know what the principal or main values are. I actually don't know it anymore. Yeah, I would have to look it up. You have to look it up. You have to know it. If you want to work with it, you have to look it up. And of course, I would look it up, but well, you do not necessarily have to know it by heart. But well, I would look it up and I would know it. I believe it's that, but I'm not quite sure. So the arccosinus would be defined that just in the same way. And what did I do here? If this was confusing, because I know it confuses students when you write this and this, well, just remember this. I wrote somehow two functions and like that, right? So cosinus went from minus pi 0 pi, sorry. I automatically always write minus pi because I like minus pi better. It makes everything symmetric. But of course, in this context, it's wrong. All right. Okay. Cosinus minus 1, it's same as arccosinus. It's two symbols for same thing. This is more mathematical. It's more engineering. Right. Another time, what did we do? We took our spiral, which I from now on call unit circle because, well, I told you how it works. We take an angle, alpha. We compute cosinus of this angle. Compute cosinus, right? Cosinus is the thing that we computed. And then what this function does, it takes our cosinus. That is, it takes the number that we had there. And it computes, that is y minus 1. It's kind of like never write that on anywhere, but never ever write that in any homework or anywhere. And this is like composition is like multiplication. But well, this is actually well, this is how you can memorize that it is cosinus minus 1, that it is written like that. All right. But actually, it has some meaning. It is not that wrong, but not at school, all right? So it is not that wrong, but yeah, it is wrong, but not that wrong. Okay. Okay. And this gives you cosinus back. That is, what did we actually do? You took alpha, you computed cosinus alpha, and we are cosinus did that. But of course, be aware. What you will get would be not some cosinus alpha. If you have an argument that you have to evaluate, that will be that, right? And then you do that from that value. But you know that there is a principal value. Principal value means this interval from 0 to pi, right? There is a principal value. So that it is cosinus of some alpha. And you know that we are cosinus for this number, which is uniquely identified with some angle, give you the angle, the principal value, with which this number is identified, which will be in this case, if I'm at 1/2, and that is the cosinus, which will be pi through. And that I just know. Of course, I have not computed it somehow, but I just remember that from what we did earlier, right? So with r cosinus, it's not like you have to compute it somehow. You know values of some angles, otherwise you know you use the calculator, but always pay attention. What angle are you talking about? Maybe you need an angle in the interval, I don't know, something like that. Then don't try there pi third. It would be complete nonsense. And of course, like minimal value of the angle that lies in here to be complete nonsense, because this is not at all in this. And don't confuse the points. The points are all the same, right? But the values, the number values, they are just like on the axis. They go and go and go. So pi third is not the same. Pi third here, and that is also here. 2 pi plus pi third is 7 pi. Sorry, it's 5. No, 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 no. 2 pi third. Okay, that's how mathematicians calculate things. You can see that in the flash. 2 pi, 6 pi, 7 pi third was so right. Right. 7 pi third is in the same point, but it is not the same angle. This angle, 7 pi third, that is after I went until 2 pi, and I have taken a turn on a spiral upwards. Right? It is at the same point geometrically in this model, but it is on the spiral higher up, so it is not the same angle. It's the x-axis drawn in the spiral, right? The angle is the same. The angle is the same, but the point is not the same. What do I say? The angle, which you would mean by that, is the same, but mathematically, the number of the angle is not the same, and the point is the same. But mathematically, the angle is not the same. The angle is the same in the everyday life. In the everyday life, you would not care if you got this angle after whatever many windings of a spiral. In the everyday life, it would be just this angle, nothing else. But in mathematical sense, it's not same number. Of course, it's not same number. Like pi-third is not equal that. And this is how you consider these numbers in mathematics. They are just numbers, and you compare them as numbers. Right. All right. Maybe let me finish here, because I realized that my videos are kind of too long. So maybe I'm overloading you, especially for school level. It might be a little bit much, even though there's nothing in it. But I realize that you have to work it out properly, and that it is actually real mental work for you. I realize that. And it is normal. It is normal. You are standing in the beginning, so it's completely normal. Standing in the beginning of mathematics, so yeah, it's completely normal. I'm not saying anything. Completely normal. I had this time too, so there is nothing special about it. I mean that in the good way that everyone has to go through that. Yeah, and you just have to think about these things. Yeah. Mm. I will, when I was in your shoes, was the same. Right. Um, Another thing I would like to tell you, but okay, since we have to recall something, so that okay, that is how the inverse functions work. You can work out that for sinus, or you could read it on Wikipedia and understand what it actually means. Actually, you have only to read on the interval and just do some examples, some exercises, so that you can come up with yourself. Just learn to use, just take angles from different windings of the spiral, like then same works of course for tangent. Again, we know where we can invert it. For example, here, very nice branch, or this branch, but I think the principal branch is this here. Exactly in the same way it works for tangent, and we get arctangent. And well, what else? Well, next time, basic trigonometric identities. After deriving cosinus alpha plus beta sinus alpha plus beta in the proper way. And complex numbers. We are finally getting to something interesting. Oh, I mean, it is interesting indeed. This here is very interesting in structure, right? But with complex numbers, you can do many things. Well, actually, we will not look at many things that you can do, but I mean, the complex numbers are now the pinnacle of what we did here in the two sessions. It's like the thing to which we tried to get. It was all foundations for it. Well, inverse functions, maybe not necessarily, but okay, maybe we'll do one thing with inverse functions too, where you will see some amazing mathematics at work. You will learn to do something that is really really like going beyond what one could think of doing at school. And so maybe we'll do that, I don't know, but yeah. I meant that we finally get into something interesting in the sense that that all was just foundations of this thing, because I'm burning to show you one view in complex numbers that is very, very important. No, complex numbers. Right. I actually don't know if I will introduce him like start, but actually with this view, it doesn't matter much because it's like um you get them just like on the silver plates. You just get them presented as something completely natural. That's the beauty of this approach. Yeah. Yeah, of course, it doesn't mean you don't have to learn how to do some things with them, but it will be just some easy stuff. It won't be any trouble after you have learned this approach. It's like, yeah, and it's really beautiful and it's really intuitive. So it's not something, oh, first I have to go through that many things. Of course, this is already something demanding, yes, but I think the level of what we are about to talk uh, about would be not higher, I think. Well, of course, it's always in the eye of the observer, but yeah, I think it won't be harder. Maybe it will be even easier because it will be more visual. Maybe here it is visual, but there's like some thinking behind it. How I think it will be pretty visual actually. So yeah, you certainly, I hope so, will enjoy it. Okay, good. And next time the complex numbers.